Now we present the method behind importance sampling. Let's first put both of the densities, the original density, which we have been calling fx, and then the modified density or the shifted density or the bias density that we saw in the movie in the previous slide, and let's call that fv, and let's put both of them on the same plane. So as before, we see the limit state function g, the limit state equation g equals 0, and the failed region and the safe region have been demarcated, and we see the two densities which are decidedly different. Not only are they centered on different regions, but I have deliberately made the contours look different from one another, because the fv density function does not have to mimic the density function of fx. So this is our original scheme, which we looked at quite a few times when we were looking at Monte Carlo simulations. So our failure probability is the probability content of the failed region, or gx less than 0, and we can just convert that into an expectation type operation if we bring in the indicator function I, which becomes 0 when we are in the safe set and which becomes 1 when we are in the failed set. So the domain of the density function now becomes the integration occurs over the entire domain of the density function fx. So this by definition is the expectation of the indicator function capital I. Now let us do something interesting, and without changing the definition or the expression for p at all, all we do is that within the integration we multiply and divide by the new density function f of v, evaluated at the same point x. So that's fine. It's something we can definitely do, but this gives us an idea, and that's where importance sampling comes in, is this now could be interpreted as something entirely different. It could be interpreted as the expectation of a larger expression, the indicator function multiplied by the ratio of fx over fv, and then the expectation in that case is being taken with respect to the density function fv, no longer with density function fx. As long as we remember this, there is no confusion, but this is a completely different way of looking at the same problem. Now we are sampling from the new density function fv, and the indicator function is multiplied by a sort of correction factor, if you will, fx over fv, the ratio of the two density functions. So the summand is 0 when there is no failure, but the summand is not exactly 1 when there is failure. In fact, it depends on x. So that IID Bernoulli sequence and all the benefits that we could get from those properties, they are lost. But still, this gives us the way of estimating failure probability, which is what we did actually in the previous example. So p hat, the estimated failure probability, would be the average of the expanded quantity I times the ratio of fx over fv, and the sampling is being done from the density function of v, fv. Then obviously we could try to find out what the uncertainty in the estimate is, and the uncertainty in the estimate would be the sum of the individual variances. The variance in p hat would be the sum of the individual variances, because the samples we are getting from FV are still IID. It's just not from FX, but still they're IID. So we can express the variance of the sum as sum of the variance multiplied by the coefficient squared, which is 1 over n squared in this case. And if we obtain these n samples, we could express the variance of p hat simply as expectation of x squared minus the square of the expectation. So the last line that you see is basically that. So this is our new estimate of the failure probability, and depending on how we choose FV, this can become quite efficient. Unfortunately, if we choose FV wrongly, then we would actually have widely incorrect results. So importance sampling has to be done carefully. The location on which you center the importance sampling density FV is vitally important. Let's look at an example to see what the result of choosing a very special sampling density function would look like. So this is the ideal case, and we can show that in this ideal case the importance sampling will have actually zero variance, and in fact just one sample would give me the correct answer. Let's see how we can create that special sampling density. So this is where we are. Our definition, our expression for the failure probability is the expectation as you see on the screen, and we estimate that way, and the mean and the variance of the estimate is as you see on the screen. So this is all we had in the previous slide, but we need to use them, so which is why I put them here on the left. And now let us see what if we choose the sampling density FV as 0 in the safe region, and the original density divided by the content in the failed region, the probability content, so that is P, that in the failed region. So, and in principle I can do this very well because I know the original density function f of x, that's what I start with, and I can always truncate a density, ignore one part, and then enhance the remaining part, amplify it so that the volume or the area under that still equals 1. So let's check if that's what's happening. So obviously FV this way defined is non-negative everywhere, so that's good. And if we integrate over all possible values of x, we still get the value of 1. So FV is indeed a legitimate density function. We also need to, let's combine the two conditions, that x belongs to gamma, the safe set, and x belongs to gamma bar, the failed set, and we can write the f of v, the sampling density, combined as the original density function times the indicator function, that x is in the unsafe set, divided by p. So that is one combined expression. Now let's just make sure that this way the expected value of I fx by fv indeed gives us p. So let us just go through the steps. If we put the value of fv as we have defined just above, then Indeed, we see that the expectation boils down to expectation of p, which p being a constant is p itself. So this way we actually are being true to the original setup of the problem. Now let us see, in this situation, the way we have defined fv, what is the expected value of p hat. The expected value of p hat, if we go through the steps, just plug in the value of fv in the equation on the left side. It gives us 1 over n times the sum of p, which basically is p itself. So we are back to an unbiased estimator, so that is great. And what would be the variance of p hat if fv is I fx over p? That turns out to be something very interesting. Is, if you just plug in the values, it's 1 over n square times the sum of the variances of p, but p is a constant, so the variance of a constant is 0, so the variance of p hat is 0, so which basically means p hat is a constant, and just one estimate of the sample is good enough for me to estimate p exactly. The problem obviously is, as you have noted, is that we don't know what p is. Our whole idea is to be able to estimate p. So even if this is the ideal situation, we can really not achieve it, because we need prior knowledge of something that we do not know.